when you have this kind of architecture, or at least the simple one I described, you eliminate the stochasticity, to use a pedantic term, in the prediction. You basically, I mean, when the system is trained to do this, it trains itself simultaneously to find a good representation of the input that preserves as much information as the input as possible, but at the same time is still predictable. So if you have phenomena in the input that is unpredictable, like chaotic behavior, random things that you just can't predict, individual motion of particles and stuff like that, from thermal fluctuation, it's not going to keep this kind of information. It's going to eliminate this and just keep whatever relevant parts of the input are useful for prediction. So, let's take a chamber full of gas and we can measure all kinds of stuff about it, including the position of all the particles, which is an enormous amount of information, which you can't predict because you have to know, how every particle interacts with the walls and the heat baths and everything. So you can't really make any prediction of that. Then probably the system spontaneously will say, well, I can't, I'm not going to be able to predict the trajectory of each particle, but I can measure, pressure, volume, maybe number of particles, and temperature. And look, when I compress, the heat goes up. So, PV equals nRT or something. That's really the essence, I think, of like where perhaps machine learning connects with science or physics in particular. Another aspect of this, which I think is fascinating, which really we haven't explored nearly enough yet, because that's kind of a bit of a new concept, is the idea of the level of abstraction of a representation. So people do this in physics, in science, right? In principle, we could explain everything that is occurring between us right now in terms of, quantum field theory, right?